we're asked to reconsider an example in the book. The problem deals with buying apricots and buying the uh, the other potassium form of the blend, which are the dried dates. Now here was the feasible region based on the equations, and in between here was the region that worked. Now we're saying on top of the above constraints, suppose that the company determines that it can process at most 10 servings of dates and at most 30 servings of apricots. So this value was our x, and this is what we were calling our y, the number of dates. Okay, well now it's the maximum number is at most 30 servings of apricots per box. So that means that somewhere over here, this is 16, so 30 would be somewhere over here, and since that's an x value, that's going to be a vertical line, and the feasible region will be this way. Now the other constraint is, and so that doesn't really seem to affect anything because this is still the feasible region. However, now we're saying that they can process at most 10 servings of dates. Well, 10 is somewhere around here, right there-ish, and if we draw a horizontal line, we now notice that we've chopped off two of the critical points, and we've added two new ones, that guy and that guy. Well, the objective function is still the same, so we definitely don't have the optimal one anymore because 0.17.3 produced the minimum cost, but that's no longer part of the feasible region. Neither is this guy here. So what we need to do is determine whether these two critical points fall under both of these costs. So to do that, we need to figure out what this point is. So the first thing we're going to do is we're just going to go ahead and plot the line, which is going to be y equals 10. The second constraint, again, does not matter because if you shade in this direction, the overlap is still in this little region here. So if I graph that, now I just need to find the intersection point between this line and the horizontal one, and then this line and the horizontal one. So I'm going to do that, calculate, intersect the first curve. I think I'll go ahead and do the horizontal line, and then it jumps to the second curve, which you can see is on this line here. So I'll hit enter, enter. The intersection point is given at about 4.9, 10. So we'll just round that up to 5, 10, since we need to have integer values. So that point is 5, 10. We'll find this one in the same way, second calc, intersect. Now we'll jump to y3 equals 10. So we'll hit enter, and we want to jump up to y2 equals this guy here. So I'll hit enter, enter, and it tells me that that point is about 16 and a half, 10. So 16 and a half, 10. I suppose we could have fractional number of servings. So 16 and a half, 10, that seems about reasonable. Half a serving seems better than having 4.9 servings. So what we'll do is now we'll test these points, 5, 10, and so we'll do 3.33, that's the number of dollars, 5 per serving times 5 servings, plus 2 times 10 servings, and let's see what we get. 3.33 times 5 plus 2 times 10 will give me a cost of $36.65. So that equals $36.65. So far, this is the winner of the top of these because it produces the lowest cost. So now we'll test 16.5, 10. We'll do that the same way. 3.33 times 16.5. And you can already tell that this is going to be more expensive because the number of servings is greater. Plus 2 times 10. And that's going to be $74.9, which is almost the most expensive route to go. So the best option is the number of servings of each should be 5 and 10, given this new constraint, so that we process at most 10 servings of dates and at most 30 servings of apricots per box, but we also meet the other constraints. Why does this numerical change take place? Well, because we've removed one of the corner points and we've reduced the size of our feasible region.